Members of the Senate of Barbados, members of the House of Assembly of Barbados, Professor Winston Moore, Deputy Principal, the UWI Cave Hill Campus, Your Excellency Ambassador Malgorzata Vascaluska, Head of Delegation of the European Union to Barbados, the Eastern Caribbean States, the OECS and CARICOM CARIFORUM, members of the Diplomatic and Consular Corps, and especially honorary consuls of European Union member states, Professor Morten Meldal, 2022 Nobel Prize Laureate in Chemistry, Dr. Phaedria Marie St. Hilaire, researcher and angel investor, Mr. Mark Hill, CEO of Export Barbados, development partners, other specially invited guests, members of the media, ladies and gentlemen, in particular our online audience, friends. Good evening. I am Dr. Janice Badnock, Senior Lecturer in Organic Chemistry and Dean of the Faculty of Science and Technology at the UWI Cave Hill campus, and it is my great pleasure to serve as your Master of Ceremonies and to welcome you to what promises to be a truly inspiring and thought-provoking featured talk about chemistry. For some of you, this is a return to the Cave Hill campus after some time, and so to all of our alumni, especially our science alumni, welcome home. Thank you for choosing to spend your Saturday evening with us. Tonight's event is the final in the Barbados leg of the Connexeus 2025 EU Caribbean Talk Series on Innovation, held over the past 3 days under the theme Bridges of Innovation. Each event in the series has explored the interconnected themes of science, education, innovation, and sustainability, woven together by a shared spirit of curiosity, urgency, and hope. And we sincerely thank the European Union for their commitment to building these bridges. As someone who spent years in the lab, surrounded by beakers, flasks, columns, and captivated by the elegance of organic mechanisms and the quiet thrill of molecular discovery, I feel a deep personal connection to the title of today's talk. Chemistry is everything. I've been saying that for years. Because indeed it is. Chemistry is the language of life. It is a science that explains the invisible forces behind visible change, from the air we breathe to the medicines that heal us, to the sustainable materials that may one day help save our planet. But chemistry is also about people. It is mentorship. It is connection. It is opportunity. It is innovation passed hand to hand, across borders, across disciplines, and across generations. And that's what tonight's lineup of speakers, and that's what makes them so extraordinary. We are joined not only by a Nobel Laureate in chemistry, whose groundbreaking work in click chemistry has reshaped how we build molecules, making it possible to join chemical components quickly, reliably, and with extraordinary precision, but also by a Caribbean-born scientist who exemplifies what's possible when talent meets tenacity. In our conversations, in my conversations with them over the past few days, one thing has become abundantly clear. They each hold a deep belief that people, not just ideas, are the true engines of progress, and that bold, early-stage ideas often spark the most meaningful transformations. Together, they represent a vision of science that is global, inclusive, and profoundly human. But this is not just a scientific talk. It is a conversation about how we shape the future. And for those of us from small island nations, developing regions, and underrepresented communities, it is also about reclaiming our place in that future. So on behalf of the University of the West Indies, Cave Hill Campus, the Faculty of Science and Technology, and in proud partnership with our colleagues from the European Union, I warmly welcome you tonight. May this evening ignite some new ideas, but definitely meaningful connections and a renewed sense of purpose in all of us. So it is now my pleasure to invite our first person to the stage. I want to invite Professor Winston Moore, Deputy Principal of the Cave Hill campus, to deliver remarks on behalf of the university, our first speaker.
Thank you very much, Chair. And allow me to adopt the already established protocol, but just say a special welcome to the ambassador and to tonight's featured speaker. On behalf of the principal and my colleagues here at the University of the West Indies Cave Hill campus, it's my great pleasure to welcome you to this session of the Connexeus EU Talk series, hosted by the Faculty of Science and Technology of the University of the West Indies, of the Faculty of Science and Technology here at the University of the West Indies. We are honored to launch this important initiative at a time when science and technology and innovation on the development prospects of small island developing states could not be more pronounced. This event would not have been possible without the generous contribution and support of our valued partners, the European Union, as well as the Ministry of Industry, Innovation, Science and Technology. Your commitment to fostering a knowledge-based Caribbean is deeply appreciated, and today's dialogue reflects the fruit of that shared vision. The Connexeus EU Talk series offers us more than a platform for discussion. It provides the space for us to collectively imagine what innovation might look like when grounded in the lived realities and unique challenges of small states. As we confront the enduring threats of climate change, food insecurity, and economic volatility, we must position science and technology as not just optional extras, but as a bedrock of resilience. Empirical evidence underscores this point. The World Bank highlights that small states investing consistently in research and development tend to experience stronger productivity growth, more robust responses to climate-related shocks, and deeper economic diversification. Mohan, Strobel, and Watson show how innovation systems grounded in local contexts, such as informed training and technology adoption, can drive meaningful gains in productivity and employment. And economists couldn't have gotten up here and said any remarks without mentioning productivity. So you're welcome. At the University of West Indies, we are proud to be part of this agenda. Our Faculty of Science and Technology continues to lead in critical areas such as climate modeling, AI, bioinformatics, and renewable energy. But I wish today to say a few words in particular about our contributions to chemistry to this regional project of transformation. Chemistry, the so-called central science, has quietly but powerfully enabled many of Barbados' most important advances in sustainable development. Our chemists working across the academic, public, and private sectors have contributed to innovation in solar energy, biomass conversion, and analytical sciences. They're not just abstract contributions, they are directly aligned with national development goals. Take, for example, the Bioenergy and Biofuel Research and Development Project, which has made strides in converting local biomass into biofuels with the dual objective of reducing fossil fuel dependency and promoting circular economic models for the Caribbean. Chemistry also underpins much of our public health preparedness. The Best Dos Santos Public Health Laboratory in Barbados employs advanced analytical techniques in molecular biology, pathology, and environmental chemistry to safeguard population health and ensure food and water security. This is science serving the people in the most direct way possible. Our research is strengthened by the partnerships we have nurtured with ministries like MIST, with regional firms in agriculture, ICT, and energy, and with international collaborators such as the European Union. These partnerships provide mutual value. Students gain exposure to real-world problems and technologies, while our collaborators benefit from applied research, innovation support, and a highly trained talent pipeline. To our students here today, your role in this ecosystem is vital. Science and technology belongs to you, not in the distant future, but right now. Engage, ask, test, build, and dream. Our job as a university is not just to teach, but to empower, to open the laboratory door, and to support you as you shape the future of the Caribbean. Let me again welcome you to this Connexeus EU Talk Series event, and I invite you to enjoy tonight's event as much as I will, even though as an economist I may not understand as much as I would like to have understood. Good night, everyone.
Thank you very much, Deputy Principal, for your continued support of the sciences. So tonight's event would not be possible without the kind support of the European Union. So please join me to welcome Her Excellency Ambassador Vaskaluska, Ambassador of the European Union to Barbados and the Eastern Caribbean, to deliver her remarks.
Thank you so much. All protocols observed. Good evening, ladies and gentlemen. It's an absolute honor for me to be here today and to host our distinguished guests. We already had a privilege to spend a little bit of time with them, and we are lucky to accompany them on to Dominica afterwards. You get this one unique lecture moment. And an opportunity to interact and ask questions, and please make the most of it. They're both really inspiring and fascinating speakers, and for me definitely, and I'm sure for many of you, it's the first time to have such a privilege to meet such distinguished scientists. The lecture is part, as you have seen, of a Connexeus 2025 program, our new idea to bring scientists and innovators to from Europe to the Caribbean, but particularly winners of Nobel Prize in Science. Not all of them have agreed yet. Professor was exceptionally enthusiastic. He has a connection with the Caribbean already. We are keen to build those bridges between our regions, to bring more and better access to technology, innovation from Europe, and to create bonds and relationships that hopefully will last beyond the visits and the brief moments of interaction. I will stop there. Maybe just to add that this whole activity is part of our Europe month. Yesterday was Europe Day, 9th of May. We were celebrating 75 years of, tabling the idea of establishing European Union. We are strong today, 27 member states, and really quite prosperous despite geopolitical challenges, enjoying freedom of movement of goods and people, and benefiting by working better and really close together. So the relationship between our union and the Caribbean obviously is based on many similarities. There will be other activities. We will have a friendship visiting for joint maritime surveillance exercise across the region. We'll be showing 2 films from Europe on the 24th and 25th. You're very welcome to join those activities as well. It's all on our social media. I'll stop there. I'm sure everybody's much more interested in listening to the professor, both professors. Thank you.
Thank you, Ambassador. We definitely look forward to your continued partnership with us. And now it is my distinct pleasure to introduce our featured speaker. Tonight we are privileged to hear from a Nobel Laureate whose pioneering work in click chemistry has revolutionized the way we assemble molecular systems, offering elegant, efficient, and reliable methods to click molecules together, much like nature does. I join you to turn your attention to the screen for a more detailed introduction, after which Professor Morten Meldal will share his insights on the theme, Chemistry is Everything, a Sustainable Future with Chemistry.
Dr. Phaedria Marie St. Hilaire is a Dominican-born scientist, corporate leader, career coach, and business angel investor. Her experience in the pharmaceutical and biotechnology sectors spans more than 20 years. Dr. St. Hilaire is a fierce advocate of diversity and inclusion and has been working tirelessly towards a more inclusive and equitable future in business and innovations.
Women are treated differently, but not just women. If you are a brown person, if you are not from Denmark, then there's a tendency that you can be undervalued. And I thought that was not really fair. And when something is not fair, then you have to do something about it.
Dr. St. Hilaire is also a business angel investor. Since learning that women and minorities receive less than 1% of venture capital funding, she's committed to helping these groups gain access to capital and opportunities. For her efforts in June 2023, Dr. St. Hilaire was recognized as one of the 10 most inspiring female angel investors in Denmark. Professor Morten Meldal is a Danish chemist, widely recognized for his pioneering work in organic and peptide chemistry. He was awarded the 2022 Nobel Prize in Chemistry for the development of click chemistry and bioorthogonal chemistry. The professor is particularly renowned for independently developing the copper-catalyzed azide alkyne cycloaddition. This highly efficient chemical reaction has revolutionized several fields.
The copper-catalyzed click chemistry is used everywhere. It's like sort of a crown jewel because it's used in material sciences, it's used in surface modifications, it's used in all sorts of medicinal chemistry today.
Professor Meldal has also made significant advances in areas such as solid phase synthesis and combinatorial chemistry. Throughout his career, he has remained dedicated to both research and teaching, mentoring numerous young scientists and contributing to the advancement of sustainable and accessible chemical methods.
Good evening, everyone. In case you're a little bit confused that there are two speakers this evening, think of it that I'm the hors d'oeuvre and then the main course is Morten. But it's a great pleasure for me to be here this evening, and I feel very honored and privileged to be part of the Connexeus project and to do what I can to facilitate the building bridges between the EU and the Caribbean.
Sorry.
These things happen, and it's not the mistakes, it's how you deal with them, right? So, it's working. So we'll continue like nothing happened. So as a Dominican-born scientist, I feel great honor and privilege to be part of this, to do my part in forging stronger ties between the EU and the Caribbean. It's something that I always wanted to do throughout my career, thinking about how can I give back, how can I contribute, and I'm very thankful for the opportunity to do that. Because I strongly believe that given the global challenges that we face, we cannot do it alone. We need partnerships, especially when you are small nation states. You really need to partner with others in a mutually beneficial and respectful way. So tonight, I'm going to talk about some of the factors that are needed to be able to create a sustainable future. Yes, chemistry is everything. It's fundamental. It fosters, it's the groundwork for innovation and eventually economic success, but it's not the only factor. So what I will do in the first few minutes, I will sort of put Morten's presentation in the context and look at some of the other factors that are very important if you want to take chemistry, innovate, and have it transform into things that are tangible and concrete and bring success and prosperity to Barbados. So we've been here for a couple of days, and I have to say I am very impressed with what I have seen and what I have heard and the trajectory that Barbados is on. We've heard about future Barbados. We went to see the spaceship. And I think these initiatives and many others are fundamental and are very crucial in ensuring that Barbados is on a trajectory to achieve a sustainable future and economic resilience. So one of the things that I will do in my talk is share from my experiences from Denmark and talk about how Denmark has built an ecosystem that fosters innovation. Denmark is pointing very, very high above its own weight in terms of the types of the success of the companies, the number of startups and the entrepreneurs that come out of Denmark. So I will be sharing some of that today. And one of the examples I will start, it's actually a food company. So how many of you know what this is? If you know what this is, raise your hand. It's not cheese, if that's what you're thinking. And it is absolutely not bleached sargassum. What it is actually microprotein. And again, when we think about the environment and how food production, in some instances, particularly production of meat, is very detrimental to the environment, there is a huge impetus to find alternative sources of protein. So this microprotein is actually quite rich in protein. It has more protein than, for example, lentils, but it also has fiber and a lot of vitamins. And so this is the product that can be made out of it. And it's made by a company called Tempty Foods. And they have formulated it in such a way that you take the basic microprotein, which is produced from fermentation, much like beer is produced, and then they mix it with things like lentils, they mix it with carrots and quinoa. And it makes a very tasty treat. I've actually tried it myself. I use it quite a lot. But how Tempty Food came to be is actually a very interesting story. And it starts with these three young girls, Anna, Cecilia, and Martina. Anna and Martina are actually not Danish. They came to Denmark to study, to further their education, because some of the opportunities were not available to them in their home countries of Slovenia and the Czech Republic. Martina is studying innovation management. Anna is a food nutritionist. And then they met Cecilia on a course, who is Danish, and she's a food engineer. So right away, you have different competencies, and it was crucial for them to have somebody who is actually Danish, because she knows the culture, and she can help them with the sales and marketing. So the idea to use the fungi as a protein source did not come from Martina. She actually got that in another class from somebody else. However, when they got together, they thought that they are going to make something out of this idea, and they moved very quickly. They seized all the opportunities there were. In 1 week, they actually made a prototype of the product, and in 2 weeks, they applied for funding, and they applied for an accelerator program, and they got in. And that was in 2021. In 2024, 2025, 4 years later, they have won many awards. Tempty Foods is well known in Denmark. It's in the supermarkets. They have partnered with some of the largest wholesalers in Denmark, selling food to canteens. And now they are planning for ton-scale production of the mycelium. The other thing that was critical, they decided that they are not going to reinvent the wheel. The first idea was that they would actually ferment the mycelia themselves. But then they found a company who's already doing it. So there's absolutely no reason to reinvent the wheel. Through partnerships, a lot can be achieved. So these were, there are three things that made them a success. One, as I mentioned, it was not her idea, but she felt no shame in building on the idea of somebody else. Sometimes we get bogged down that it's not my idea, so I cannot do anything with it. The second thing was that they moved really, really quickly. And then the third thing, which is what I'll talk a little bit more about, is that the whole entrepreneurial ecosystem in Denmark provided them in many opportunities. So what are some of the elements of that ecosystem? It all boils down to having an excellent STEM education with focus on chemistry and biotechnology and physics. And the system, it's well-funded, it's free, and there are also many other initiatives to encourage women to participate or choose STEM subjects. But I will not go into too much detail because Morten will talk a lot more about this in his talk. But I will just say that research has shown that countries that invest heavily and focus on STEM subjects, it contributes at least 1% annually to their GDP. They are extremely successful countries. Another factor is collaborations and partnerships. And these are absolutely key. There's absolutely no reason for a company or startup or an institute to do everything themselves. There's no need to have duplication. Through collaboration, and where each person brings their own form of expertise, you can actually go extremely far. And this way of collaborating, it's something that's embedded in the Danish society. Kids, from the time they are in kindergarten or first grade, they start working in a project-based manner in schools. And between the Nordic countries, in Finland, in Norway, in Sweden, Denmark, Iceland, there's a lot of collaboration and exchange of information and knowledge. So having collaborations and partnerships between industry and universities are key. And if we think of Barbados, I know that there are some of these things happening, but I think we also have to think of critical mass and see whether can we extend this to the Caribbean on a whole. Right? So we can have partnerships with EU, but I think it's critical to have inter-island partnerships and collaboration. Another factor is having innovation hubs and accelerator programs. Martina and her team at Tempty Foods, they quickly got into an accelerator program, and there are several of these at many universities in Denmark. Practically all the universities have innovation hubs and have accelerator programs. This other thing was that they also got funding. And I will speak a bit more about that, but many of these innovation hubs, they are funded by the government, but also by private partnerships. Then, if you want to promote innovation and entrepreneurship, then you need to have the right government policies. In Denmark, the policies for investing and founding, they were not the best, and actually last year there was a reform, and some of the reforms that were made, for example, to start a company in Denmark, the founder needed to come up with about 7,000 euro. However, due to the reform, only half that amount is needed, so making it easier for people to start companies. Another very, very important reform has to do with the taxation. The current practice is that as soon as a startup starts making revenue, then they get taxed on the revenue. Now the government has instituted a policy where the taxation of the revenue is deferred until the startup is actually profitable. There are also incentives for investors. One of the key things about investing, and if you think about angel investing, which is very critical for the early stage, it's that if you are funding huge initiatives, especially in biotech, then you might need several angel investors pooling money together. And there was a restriction that you could only have 7 people making a special purpose vehicle for that particular funding. And so you might end up having to make 3 or 4 vehicles to be able to have sufficient money to make the investment. So now they have abolished that limit for 7, and so there are a larger number of investors can come together and making it easier. So it's a question of making the processes transparent and easier to be able to incentivize people to be founders as well as to be investors. So it's very important that the policies that are made are sustainable and that they outlive and transcend political parties and election cycles. Then the last one I will talk about is funding. Without funding, chemistry, everything, innovation can't really move forward. And there are many different avenues for funding. People traditionally think about getting venture capital, but you also have loans, and you also have what we call soft funding, where you could get grants. And of course, you have angel investing. I will talk a little bit more about angel investing because it's close to my heart, and it's what I do. And also to emphasize the importance of angel investing. Of course, sometimes you want to have a grant program where you need a lot of resources, a lot of investment capital. But sometimes for a startup, especially in the early stages in this valley of death, just to get the idea off the ground, this is when you will need to have angel investors. And to give you an idea of how critical angel investing has been, I will highlight 2 success stories from Denmark. The first one is Trustpilot. How many of you have heard of Trustpilot? Right, I think many of you have heard of Trustpilot. It's a platform where you can evaluate different services from a multitude of companies. That was actually started in Denmark, and some of the first angel investors was a syndicate or a group of angel investors from the largest angel investment community in Denmark called Danban. Another one is, did somebody say Just Eat? How many of you have heard of Just Eat? So Just Eat is a platform where you can order food online and have it delivered. But that's what it is. And you might think it's such a simple idea. Why didn't somebody think about that before? But it's sometimes just the simplest of ideas that become huge successes. So the founder of Just Eat, again, he had angel money that tided him over for the first 5 years, and then now it's actually a publicly listed company. So angel investing can actually catalyze sustainable growth, especially critical in the valley of death. And this is where I think there's a huge opportunity for angel investing in the Caribbean. We could tap into the diaspora as well as people here who want to do angel investing. Of course, usually it seems very daunting because it is high risk, but if you learn how to do it, then it's definitely something that can help catalyze sustainable growth in Barbados and in the region. And those were my last words. I will now hand over to Morten, who will talk more about STEM education and chemistry.
Thank you very much. Thank you to Connexeus, and thank you to University of West Indies for this honorable invitation to come here tonight and talk. And thank you to Phaedria for introducing the subject. So in 2022, I got a phone call from Sweden, and I saw the Swedish number on my telephone, and I thought, well, this company has tried to sell me instrumentation for a while. So I go, yes! And the other end, there was pretty silent actually in the other end for a while, and then they said, this is a Nobel Prize committee, and so on. And then I was very silent from my end of the phone because I answered so briskly initially. But this was the information that I got the Nobel Prize, and I was not allowed to say anything about that for a whole hour. That's probably the longest hour of my life. And then I went out in the corridor, and there was people everywhere, and it was a big celebration. I received the Nobel Prize together with two friends. This is Barry Sharpless and Carolyn Bertozzi, and they are very good friends of mine, so I'm very happy to share this honor with them. When you get a Nobel Prize, you are asked about your opinion about everything, right? I don't know about everything, but I do know that chemistry is everything. And as we just heard, it's literally everything. It's the air we breathe, it's when we fall asleep, it's when we are hungry, it's everything that happens inside and outside of our bodies. So for that reason, it would seem quite important to start very early on in the childhood with the teaching of this. If it's really everything, consider it. If it's really everything, why don't we teach our kids this from the very beginning, right? And the way to teach this is not by the way we do it today with formula, two-dimensional and kinetics and molar calculations and all of that. No, it's a three-dimensional world. We have to dive into it. Give the young people a real experience that they can feel associated with, that they can see and navigate inside. So I'll talk a little bit more about that. And then I have two more mantras. One is research with no constraints. I'll get a little bit to that. And research funding by performance. So I will continue from where Phaedria left off by saying that investment in education is probably the most valuable, societally valuable investment you can do. So education comes back with much more return on investment than any other investment you can do. So it's the most impactful long-term investment in the society. It drives innovation and growth, and it enhances social stability. Countries where this is prioritized, they experience much higher GDP growth and improved productivity and greater financial resilience. This is not something I invent here. This is actually described in reports that calculates this in detail. Science skills correlate with long-term economic growth, and particularly in the STEM area. So you get social cohesion, you get political participation, you get overall well-being and sustainability in the population. And the positive externalities of that is benefits extend beyond the individual to society as a whole, which is very, very important in the educational system, that you extend the benefit not to a particular person who owns a company a billion worth, but it's actually spreading out in the society as a whole. And while infrastructure, healthcare, and technology investments are, of course, crucial, education uniquely empowers the innovation, adaptation, contribution, and multi-sector cohesion. So meaning that the different areas of society can collaborate, the different societies can collaborate. So this is actually proven. The educational system has been upgraded in Finland, South Korea, Vietnam, Denmark, and Poland with very good success. Really incredible return of investment in these countries. And these are the reports behind it. So the societal consequences of giving education in chemistry from very early on is that chemistry gets a thumbs up, first of all, in society as a whole. It's a tool for societal progress for everyone. I mean, a craftsman that works with concrete, he needs chemical knowledge actually to do it correctly. Climate issues and environmental issues are extremely important today. They can only be understood through chemistry. We can only make the right choices if we know this chemistry behind it. So on the individual level, we get also the opportunity for understanding the resources and understanding the limitation and the sharing of resources and how we can collaborate on that and get the most out of it. In competition, you're always fighting other people, and it's always ending with somebody losing. In collaboration, everybody wins. Yeah, so there's one thing about the return on investment, and that is it takes a long time. Education is a 20-year process, and it's difficult to control. Where does it go? If we send somebody to Europe, which I highly recommend for young people here in Barbados, to take contact with the universities in Europe, which are just as high in standard as the US, Canadian, and UK universities. And we actually speak English. So get to Europe as a young person in Barbados and get this knowledge that some of the best universities in the world are there, unexplored from Caribbean side. And it takes a long time to get the education going, and it's difficult to control. They might stay in the European country afterwards, but then you can produce incentives to return. Right, so that I think is very important. They also require immediate investment, so the whole society has to get together. The tribunal of the government, the industry, and the educational system get together and decide how do we actually make this investment so that it works for the future development. And also it's unspecific to the investor. So the investor has to be a little bit philanthropic if it's a private investor in order to get into this business. Well, shaping of talents. There are many factors that influence the choice of education and the shaping of the talent. These are knowledge, of course. If we can make the students know something they can be interested in, you have the parental and institutional influence, which also is very important. And we should be very careful to give the young people enough courage, enough freedom to make their own choices, because it's only through own choices that you really can bring this forward. So you need courage and opportunity. Status and salary is another way that you choose your profession later on, but status and salary is probably not the most interesting for good life. For good life, the most interesting is that you work with something you're curious about, that you like to do. So existential curiosity is, in my opinion, the most important factor for making your choices. And the education is also depending on our creation of identity in the young people, and they start very early. So identity is not something that happens at the time where we are making the choices for our education. It starts when we are 3-4 years old, and it builds up very, very strongly over the coming years. It's largely emotional. A lot of it has to do with emotion. So we should give the STEM area some emotional value for the kids. And if we do match the needs correctly, if we do match the interest by the young people with the societal needs, we can really achieve something. We should remove external pressure, balance the knowledge that we give them with authority, and give a positive reinforcement and self-esteem to the young people. That's really powerful for development of society as a whole. because excellence, there's a few people that are really excellent, but the excellence is not limited to those people. Excellence is limited to the environment. A new entrepreneur, an investor, or whatever it is that has excellent power for putting this excellence projecting this excellence into the environment, can make a playful team at a well-equipped playground in university, for example, and give freedom to everybody in that group. Then you can have research, and you can also have innovation that is driven by the curiosity to give a true engagement so that you actually dream of it at night. You cannot stop thinking about it, and this is what is needed if you want to drive things forward. So you get independent co-workers. You have to give them freedom to do what they need to do, and you have to do all of this without losing track of where you're going. So in Denmark, we have about 15 companies here that are the leading companies in Denmark. Novo Nordisk stands for about 10% of the GDP of Denmark, one single company. Then you have Novozymes, Leo Pharmaceuticals, Lundbeck, etc. All very big companies starting almost in a garage and becoming these large companies. And they are all based on chemistry. All of these are based on chemistry, and they are sort of probably 50–80% of the industrial Denmark. They work in different areas. All of this is chemistry areas: medicine, food sector, energy production, agriculture, and so on. All of that is chemistry. And I think this is a nice model to look for if you're looking at how to develop the industrial sector here in the Caribbean. This is me, about 8 years old, no, 10 maybe. I was very lucky. I was privileged to have this farm on an island in the Baltic called Bornholm, which is my grandfather's and grandmother's farm. I was brought there every time there was a long weekend. I was shipped over there so my parents could be alone. And I was let out at 7 o'clock in the morning in this beautiful place, and then I came in at 10 o'clock at night. I started wondering, playing in this beauty, what is it that makes everything click so well? What is it that makes the chemistry that makes this work? I didn't think chemistry at the time. I just thought, what is it that makes this work? But of course it's chemistry. The bugs are full of chemistry, and they are sniffing the plants up with chemistry and so on. The roots are communicating with chemistry. So this is all chemistry, and this is where it starts. Early on in childhood, intuition, imagination, association, observation, all of these are extremely important skills. Today, it's not so important to have a rigid education in knowledge, because knowledge is so easy to retrieve from the internet, from the AIs, from all the tools we have at hand, that it has become there's a change to what is really important. In order to be an excellent researcher with new ideas, it's much more important to be able to imagine things in your head and associate the imagination that you have from one thing to the next. And then you need courage as a researcher, in particular because you are sort of on your own, doing research in a new area, and you are responsible for that area. So courage is very important for the young people starting in research. Factual knowledge, less so. So this is, of course, very beautiful, but here is where I really got my inspiration at 15. This is when I took a big cardboard box and I went to a company south of Copenhagen, and I filled it up with all sorts of explosives, took the tunnel train back to my parents' house down in the basement and started mixing all of these things. And I made really fantastic firework out of it. That went all well about 1.5 years. And then I thought that I would try to make something really spectacular and make a Roman light about this dimension. 1.5 kilo of gunpowder in there. And I lit it up, and it made a very beautiful fountain of firework. Halfway down, it formed a cement on the top, and when you enclose 1 kilo of gunpowder in a closed compartment and light it up, it makes a huge explosion, and there was like a crater in my parents' garden, and that was the end of making firework in the basement. So the road to success is never straight for young people. They start up in science, and they really have to be persevering. They have to show perseverance in order to succeed. They almost fail the projects initially. You design a project behind your office desk, you go into the laboratory, it very rarely works the first time, and that's because nature is much more complex than we anticipate as scientists. We try to explain it in positivistic terms very simply, but actually it's very complex. So you should look for opportunity instead, and its time is very precious, so you should really think about how you do your development as a researcher. Get out of your comfort zone, change your field occasionally, and bring experience to use. These are my own philosophical experiences of life, and also study for the rest of your life. Don't quit studying, because there's so much to learn out there. So this here is T-Rex, Ronald T-Rex. Ronald is not burdened by heavy social skills or empathy. He is controlled by these small molecules. They are catecholamines, adrenaline and noradrenaline, sending the blood to the muscles in the legs when he sees a prey. And that satisfies then when he eats it, this small brain, the size of our brain, but the animal is 100 times larger. So it should have a much larger brain, actually, to function properly as a societal individual. But when he catches his prey, he gets satisfied with dopamine, and he looks for the next prey, and the cognition molecule here is the serotonin. So these are simple molecules that control the dinosaur brain, and it looks like that. The dinosaur brain is the things in the center here, and the rest is our brain that we developed to be able to function as individuals that collaborate in societies. And these are controlled by much more complex molecules. First of all, we get the reward, the same reward as the T-Rex. When we do something good, we get a rush to the frontal cortex of dopamine, and we feel good. And that's also one of the things we try to mess with when people take drugs. They take drugs that mess with this balance. Then you have the serotonin pathways that leads to memory, processing, sleep, and cognition. So all the things that are necessary to navigate this world. These are the simple molecules that come from long ago. So these are the molecules that are very important for us. This is a love molecule, also called oxytocin. Oxytocin, if we draw it for the students, it looks like that. If we draw it as we would like to see it in 3 dimensions, it looks like that. But in reality, it looks more like this. Chewing gum with colors. That's a molecule. The nuclei are situated inside this cloud of electrons. Some places, the blue ones, there's less electrons, and some places, the red ones, there are more electrons. And positive likes negative, so the more will interact with the less in another molecule in order to recognize it. And that's exactly what happens with this one. It sits up here in the top of a receptor molecule that sits in the membrane and sends a signal into the interior of the cell that then starts signaling into the cell nucleus, and you can have all sorts of expressions of proteins, effector molecules, and so on. You can also have a calcium rush initiated by this kind of interaction. And then you start feeling empathy and love, pleasure, and nesting and many more things. So that's this molecule. And you can see nature is very cheap, because nature took this love molecule and it just changes 2 small residues here, and then it has a molecule that can control the blood pressure, vasopressin. I would like to study those molecules when I was young, and those kind of molecules, peptides. And I built a laboratory here, Carlsberg Laboratory, where we made the polymers, and then we made a huge number of organic chemistry reactions, function quantitatively on the solid support, and we could use that in assays. These resins are like sponges that swell up in enzyme buffers or organic solvents, so we can do both chemistry and biochemistry inside these small beads. So this is kind of a platform that we built in order to study molecular recognition, molecular processing, molecular signaling, molecular replication, and molecular materials. And that is actually what compose our life. So this is a very broad definition of science. And we built this platform. First of all, we did combinatorial chemistry, which is like taking a principle from nature, like the immune system, which recognizes a foreign organism and amplifies what is active in the recognition. Here we do the same kind of thing. We make 1,000 or 1,000,000 molecules on small plastic beads, and then we test them with enzymes. As you can see over here, there's a picture with a lot of green beads and some blue beads. The blue beads are active substances with this enzyme. We take them out and identify what is the active substance with this enzyme, and then we know what the enzyme can do. We have then isolated it and made the small substrate that is on the bead, and here it's in the mouse foot to indicate the enzyme that is active to arthritis. We can grow cells on the beads, and we can identify signaling molecules and so on. We have a whole technology platform that we are taking into use in order to study biochemistry. During this period, we worked on this molecule here. We tried to take acetoacid chlorides and use them for acylation reaction of very difficult acylations, like this peptide here that can only be synthesized in this way. We thought this is a good reaction. Maybe we can use that also for what we call C-nucleophiles. We take an alkyne, make the copper salt of that, react that with the acid chloride, and that give us then an alkyne, or should give us an alkyne like this, which we could use to incorporate into peptides and make something similar to a Ozempic, very nice molecule that we have today from Novo Nordisk. But that did not succeed. Christian Thorne, who was my PhD student, came to my office and said, your ideas don't work. I want to work with Novo Nordisk instead. And he is on Novo Nordisk today. But I said, let's just look at it. And I convinced him that this is actually not so bad, because here we have what happened. We got a 5-membered ring. Instead of reaction with this very reactive acid chloride, we got the triazole, a single molecule, as we can see in this whole HPLC. And Christian took that to San Diego and presented that in 2001. And we had a publication that described that as well. So that was the beginning of click chemistry. But what is it actually? So here we have this triple bond between 2 carbon atoms. So that's 6 electrons between 2 carbon atoms, a lot of negative charge. So this negative charge is looking around for something to combine with positive charge. Negative likes positive. That's the basic theme in all chemistry. So here we have negative as sitting, a positive ion sitting on the negative cloud. What happens here is that it sucks out electron density. That makes this white proton make it acidic, and the copper takes the place of the proton. Boom. That's not enough. Not much happened here. But then it has a friend that comes in, and it peels off the electrons from the alkyne so that you get access to the positive charge. And that's what happens here. An empty electron cloud, or an empty orbital, which is like a balloon without electrons in it, and it's looking around desperately for electron density. And it comes from out here in the shape of the A side, which has exactly the correct geometry and phase of the clouds to deliver the electrons into the empty orbitals. So here we are not having a 2+3 dipolar cyclodistion reaction. We are rather having a reaction that gives us this metal cycle that then lose first one metal, then a second metal, and then we have the triazole. And now Christian is very happy because he's actually leading the click chemistry department at Novo Nordisk. So this is the first day in the Nobel Prize week. You get to sign a chair and you get to deliver something that was very important. This is a small equipment I made in my neighbor's garage that allowed us to do these millions of compounds by combinatorial methods. So this is now in the Nobel Prize Museum, and so is this chair where I have my signature between Jennifer Doudna and Emmanuel Charpentier. So that's a very nice position on a chair that is now in the cafeteria. These guys here, there's some examples of click chemistry coming now. These guys here are 400 million years old. Well, not these guys, but the species is 400 million years old, delivers a beautiful blue blood, which is like a pharmaceutical factory of antibiotics and molecules that can entrap foreign organisms. So it's actually harvested in order to investigate whether we have bacteria in our blood. But it also has these antibiotics shown out here on the right side. And we were very interested in seeing, because they have this structure here shown with one-letter codes for amino acids, like a beta hairpin with two bridges made from disulfide bonds. And we are replacing those with triazoles to see if our triazole chemistry can be used to replace the natural disulfide bonds that is in all our proteins. And during this, we also found that these molecules form a dimer. So two of them comes together, hide away all the terrible parts, and it's benign, floats around in the solution. And then when they see a cell membrane, they aggregate on the cell membrane, attracted by the negative charge on the cell membrane, and they form a pore in the cell membrane where all the interior of the cell can escape, and then the cell dies. So that's how these antibiotics work. So this is our theory. Did it work? Here's 4 bacteria that we tested: coli, staphylococcus, salmonella, and bacillus. And in 3 of these, the natural worked. So the smaller the cone is here, the better the reagent is, better the activity is. And you can see the natural one in the front line here, the target place in 1 is active in 3 of them and completely inactive in bacillus. Our molecules, on the other hand, are actually active, both with a longer and a shorter bridge. They are both active in all of these bacteria. So it seems that we can avoid the resistance to this antibiotic by making the substitution of the disulfide bonds. And our molecules are active after substitution of the disulfide bonds. So we are back in Stockholm here. This is the day where you give the lecture. You're pretty nervous because you're talking to 10 or maybe more million people around the world, but you get over it, and we all gave our lecture, and here we all are very happy together. So this was a very nice day. I talked about molecular recognition. molecular recognition is done in life. It's done by the master, which is the antibody, and the antibody has these binding sites, but the protein itself is 150 kD. I'm in a synthetic lab. I cannot make a molecule that weighs that much. It's a huge molecule. So what could we do? Maybe we can make something that looks a little bit the same and just cut out most of it. So this molecule here has a triazole bridge, as you can see. It has a turn region, and then it has two strands. So that's a beta hairpin, which is stabilized by the triazole and by the blue residues on the top, allowing us to change all the red residues just as we please. We have done it over here, and you can see the chewing gum molecules on the top and the bottom, and one in the middle. The top and bottom one is the one that we're actually modeling in our computers. So we do a modeling of this recognition, and then we synthesize it, and then it's active. Because when we mix the two blue and red molecules, you can see nothing. Then we add the green and orange molecule to the solution at very low concentration, and then it traps. First, it's trapped in the bead, in a small particle, and then it extracts the fluorescent molecule from the solution. So we have here proof of two recognitions made by a single modeling and synthesis at very low concentration of the protein. So this works just as well as antibodies. I don't have time today, but I can also show you that it's just as selective. So can we use this for anything? Alzheimer is a huge problem. 65 million people are affected, not only diagnosed, but affected by Alzheimer today. This is a plaque, and from this plaque we can isolate fibrils, like the one shown here. This is two stacks of of peptides, and these are the source of the problem in Alzheimer's disease. So they form these plaques, and the structure has been determined. So now we can take that structure and use that to see if we can inhibit the fibril formation. So we cut it open like that and get the surface, and then we can design the molecule that goes into the surface here. And maybe that can stop the fibrillation process, because then the molecules cannot stack. So we synthesized two of those, designed and synthesized them, and lo and behold, this is normal. The lower one is a normal fibrillation curve. The upper one is what happens if we add our two peptides. So we can actually block it. It's not perfect because we start getting some fibrillation and you never know. So we would like to improve that a bit. But we did see that if we add this peptide to the already formed fibril, we reduce the fibrillation quite significantly. But my PhD student, Yuan Zhang, he took glucosamine that has the same configuration as the blue residues that you saw on the first slide of this. And he incorporated those into peptides by protecting the molecule and using it as a building block. Why would we do that? We would do that because we thought then that would interact with water. If we look at all these hydroxyl groups that we have on this molecule here, that would interact with the water and bring a shell of water molecules with it into the recognition process, which is exactly what we want. So here we have synthesized 5 molecules that we have designed by computer, and now we are looking at what happens. They look like that, by the way. This is the sequences of these compounds, and you can see they are not anything like a normal peptide if you know anything about peptides. If you don't know anything about peptides, you can't see anything by this. So here they are, and the upper curve is the free fibrillation that these Alzheimer peptides do. We can measure that by a fluorescence technology. And if we add our 2 molecules, you can see here the best ones 3 plus 5 give absolutely no, that's the lowest curve in both cases, give no fibrillation whatsoever. So that is a very powerful technique for hindering the fibrillation, the precipitation of the plaques in the brain. And we think that is what happens. You have the water shell with the blue and red molecules that go in and bind to the end of small fragments, and then we can probably wash it out during our deep sleep at night when the brain shrinks and pushes out all the debris from the day. Here we are back in Stockholm, and this is the day where you get the Nobel Prize. So the king come forward and you get the Nobel Prize, and you thank the king, thank the audience, thank the committee, and then you go to your place. You're not getting actually the medal that day. The reason you're not getting the medal that day is because it usually takes about 20 years to get the Nobel Prize from when you made your invention. And during this period, a lot of us have lost most of it in the meantime. So the Nobel laureates actually forget the medals in the ceremonial hall. But you get it on the last day, and then your family can help you get it back home. So that's a small story. Here is again a little bit more about Alzheimer. This is quite an important story actually. I had a postdoc called Martin Wolfram who worked in a lab, and he was trying to make molecules that can cleave the Alzheimer peptide. Because if we cleave the peptide, it won't be able to form these fibrils. So he made a substrate that looks like the fibrillating peptide, and then he made these ones that could recognize them, that binds to a metal. So they have a carbene in the center of the peptide binding a metal that could then help hydrolyze the molecule, and it worked amazingly. That was really fantastic. So we found a molecule that could hydrolyze the Alzheimer peptides, we thought. It worked really well also with this molecule, but then Martin started to reduce the amount of catalyst for this reaction, and he reduced and still worked. And in the end, he took it out completely, and it still worked. So here is when your observation is very important, because normally that would mean that you just trash the experiment and then you'll find something else to do. But here's an important observation. It is doing this all by itself. So there's a process in the Alzheimer which leads to self-degradation of the Alzheimer peptide. That is very promising for the understanding of what goes on. So it's very specific here in the nucleation site for the fibrillation. This is where it cleaves. It has 4 cleavage points initially. And you can see here the red line is our starting molecule. And you see first 1, F0, then F1, then F4, and then F6 is formed during this process. And we know exactly what it is because we follow this with mass spectrometry. We can even take a small active mixture from up here, 1 microliter, 1 milliliter of another peptide down there. After a certain lag period, it starts hydrolyzing itself. This much longer peptide starts hydrolyzing itself, and we get complete hydrolysis. Even with the full-length Alzheimer peptides, we see this. So this here is a beta 1 to 40, one of the long peptides. And you can see after 12 days, nothing happens on its own. But if we add 1 microliter of this mixture up here to that one, it hydrolyzes completely in 12 days. If we leave this full-length Alzheimer peptide for more than a year, it starts hydrolyzing. And this is very reasonable to think of because when you get Alzheimer, you can have it a number of years before you see the symptoms. And we think this process relates to the death of the neurons in Alzheimer. We also saw something else. When we took this and seeded on mica plates and run atom force microscopy. That's a small needle that goes down and feels where the molecules are. We could see that the process of the fibrillation. First, we form a donut. So these are the peptides that are stacked around like that in a donut. And then the donut collapse, you can see over here, like a key. That's a donut that is collapsing into a dimer, fibril, small stick of fibril. And then these sticks find each other. You can see a train of sticks over here in the middle. These small sticks find each other, and eventually the fibril is maturing. So this picture alone shows the entire process of fibrillation and how we can intervene with it. So there was an important paper in 2015 by Lishinska at Allied in Nature Communication, where they found that NCAM, which is a surface molecule from neurons that keeps the neurons sticking together and perform healthily, these molecules were cleaved in the presence of Alzheimer plaques. They were cleaved off, and that's where the neuron actually die. And you could co-localize these fragments with the A-beta. So if we took antibodies that recognize both molecules, they would go to the same places, which means that it's probably the A-beta that is responsible for the cleavage, and that would fit extremely well with the two sequences you see down here. The first sequence, the upper sequence, is the one from the Alzheimer peptide that cleaves. The second one there is the one from the NCAM2 molecules, the large molecules that sits here on the surface of the cell. So there's a good chance that this process is actually one of the major reasons for neuronal death in the presence of Alzheimer. So we have the formation of the oligomers, and they form these kind of structures. This is only a visualization. There's nothing scientific about this. But here is a cavity that probably could fit in with the molecules and act as an enzyme with the carboxylate, we believe. So that could be also of significance that we have these kind of proteolytic activities that are quite strong from just aggregation of peptides, because that could be the first enzymes in biology, actually, many, many billions of years ago. So, back to the teaching. I think it's very important to teach this kind of chemistry to the students, but start out very early with just two hydrogen atoms that binds together, goes down in energy because they make the bonding, retrieve this energy by bringing oxygen in and burning it to water, retrieve the hydrogen again from the water molecule, and so on. So this is what we should teach the kids from very first grade, visually, by calling into this repository of teaching material that is very consistent, made by scientists, didactic people, and animators to make it entertaining, and give that to the children instead of what we give them today. So this would bring in an understanding in addition to the case stories that we want to present them with, to excite them with the experiments. But this is the understanding. This is where we should, how we should teach them, because we are reaching them there on their own level. And we can translate this to any language in the world and make it global. So this would be good for all of these issues which we are facing at the moment. So when the young people have to choose something, they should choose something that means something to the society. So we think new sustainable materials is very important. Processing in the industry, find new ways to do that. New catalysts, like I heard the other day about a catalyst that can directly take the photons from the atmosphere, from the sun, and transform this energy into hydrogen from water. So no steps in between, just sunlight in, hydrogen out. That would be amazing. Food, new ways of making food from Zaragoza? No, Zaragoza. Yeah. Maybe you can make food of that. Bamboo and new transportation systems. But I would like to just talk a little bit about sustainable materials. Here we have a ton of barley straw. There's 500 million tons of barley straw on the fields in Denmark, and they are largely burned today. But here we took a ton and we milled it. So this is a milled material. It's shown here below as fibers. We put chemistry on the surface of the fibers, chemistry that can be polymerized. And you can see the difference between a polymer that is not treated with this chemical and a polymer that is treated with this chemical. Is completely water repellent because of that. So the process means that we take the straw, spray it with sodium hydroxide, wash it, dry it, acrylate it, and polymerize with pressure. When we do that, we get a completely compact material with very, very good strength properties. So a wooden beam of this size could be made by this size with this material. And it can be made with any kind of fiber. So you can take banana, sisal, hemp, manila, coir, coconut, whatever you want, and do this process. We have actually combined different kinds. It's a huge industrial equipment for producing acrylated fibers for this compression technology. And that's what it looks like. So it's sort of like a plastic. I wouldn't mind having a computer with that as a surface. Then the funding. All great discoveries are serendipitous, because if we expected the discovery, it would have been done for a long time ago. So it's something surprising that is a new discovery. And if that is, you can just look at all the Nobel Prizes. All of them essentially are disruptive, HOSA, kind of discoveries. And we want, of course, the funding to be productive and quality, creative, novelty, responsible, and translation into society, into production. But today, all research is in one big box. All funding is in one big box, which is wrong, because there are two functions here. One is the fundamental science, and one is the applied science, and they are so different. The financial people do not really understand that. These are so different, and they need two different boxes to be financed that are completely independent of each other. So the thing is that all discoveries are afterthoughts of something we observed. And that's all of these, for example, huge impact on humanity, but they are all discoveries that are serendipitous. So we have two completely independent things: the disruptive discoveries that needs this kind of money, fundamental research money, in order to secure tomorrow, and what we need to develop society today. These both have to be there. So now we are back in Stockholm, and this is the wonderful day where you go to the ceremonial dinner for 1,300 people. In order to do that, my wife, she called up the arts department of Stockholm University, because the first day on the Nobel Museum, she had spotted this dress. So she said, I want this dress in 24 hours, but it's not my size. Can you make it? And they made it actually to her. And you can see that it's artist, because all of these rings are 6-membered rings. Yeah. But she looked beautiful in that dress. And when you dress your wife that beautifully, there's a danger. And here's a danger. The danger is called Prince Philip of Sweden. he separated us, and he took my wife, and she was seated between Prince Philip and Prince Daniel, and I was down by the entrance. But I was okay, because the next day we were at the royal castle, and this was an intimate dinner with 130 people. And there, as you can see on my goofy smile here, I got the hot spot besides Victoria, the coming Queen of Sweden. So with that, I think I would like to thank you, the Danish National Research Foundation, Carlsberg Laboratory, and University of Copenhagen. I would like to thank Klaus Bock, who helped me a lot. He was my mentor. And Christian Thorne, who was my PhD student, and today is Novo's head of click chemistry. Carlsberg Workshop, that helped us with making equipment. And Combio, Versamatrix, Carlsberg, and Betamap are companies that are actually innovative results of all of this research. Yes, and then I would like to thank my collaborators, people from outside our group that we collaborated with from all over the world, and the people from Carlsberg Laboratory that is now, many of them, having leading position in the Danish industry, controlling all the cash flow into Denmark because of their chemistry education. And then all of the people at Copenhagen University also having very important positions in the Danish industrial landscape. And finally, Phaedria, Ajani, Anna, and Sandra, my family. I'm very happy that they have supported this wonderful travel, this wonderful journey. Thank you very much.
I think that you can join me in an even more robust round of applause for our two speakers. And while we're getting started, the setup for our question and answer session, I want to just summarize some of what I heard. So Dr. St. Hilaire, thank you so much for your presentation. You grounded us very strongly in what it takes to take the science into the innovation space. And I heard in particular that angel investment can represent a key input that can drive the development of a complete innovation ecosystem, especially when you couple it with a robust regulatory framework encouraged by private-public academic partnerships and grounded in, and I heard that in a large way, collaboration. And then Professor Meldal, you took us on a journey of over 20 years and really talked to me about how we can introduce chemistry earlier in a manner that de-emphasizes factual content but encourages engagement with three-dimensional world and encourages curiosity using tools like animation and video and virtual and augmented reality. And the inclusion of modeling, I heard, in a very large way in the advancement of the utility of the click chemistry, especially towards the study of Alzheimer's. And I think we also heard about the green science. I'll call it green science broadly. And I think that that's of particular interest to us, where sargassum may be the source for us. But then for my chemistry students, I think you saw some protecting groups. So I saw FMOC and TESS, and the biochemists saw a little bit as well. So please join me back on stage. So Professor Morten Meldal, Dr. Phaedria St. Hilaire, and also joining us to moderate the question and answer session is Professor Avra Williams from the Department of Biological and Chemical Sciences in the Faculty of Science and Technology.
Good evening, everyone. Can you hear me? We can hardly see you because the light is like all over here. So first off, I want to say thank you all very much for your lovely presentations and for sharing your insights into the role of chemistry in building a sustainable future. As the audience would have seen, the work that was highlighted tonight can address the innovations, can address challenges, whether they be environmental, whether they be biological, in practical ways. And this is always what scientists tend to be working towards. So I must admit, however, that I have utilized click chemistry, very much so. But the first time that I encountered click chemistry, it was for selfish reasons that I used it, because I wanted my reaction to be quantitative, meaning I wanted something easy and practical that would give me almost 100% yield, because in the work that I was doing, there was no space for side products. That just brings difficulty and complexation. So I just wanted something that was quantitative. So I'm happy that coming out of this lecture tonight, I saw the other side of it, and the passion behind the click chemistry and how it can apply in different areas. So we are now going to move on to the question and answer session. And I do see Bailey, some scientists in the room. I see the students, and they are at the back of the room as per usual, just like when we are in the classroom. But I also know that we have a very diverse audience, and therefore I expect questions from different perspectives. So don't feel that you have to ask a question on chemistry. You can ask a question on what you saw tonight on the slide, or something that has been bothering you that you would like one of them to answer, not me. Yes? So, for those of you here in person, if you wish to ask a question, there are microphones on either side of the room. So please utilize the microphone so that we can hear you clearly. And you are free to introduce yourself if you wish to do so. Who wants to get the ball rolling? There's no one standing up and heading towards a microphone. Don't be shy.
There's no stupid questions.
No? Okay.
All questions are good.
So,
I'll get us started.
excellent.
So,
Go ahead, Dean.
Phaedria, you spoke about angel investors. To what extent those investors are an important part of the innovation ecosystem in Denmark? And then how can we bring angel investors from those more developed countries to smaller states like Barbados?
Angel investors, they're extremely critical and a vital part of the Danish ecosystem, because very often when a founder has an idea, they will need some capital to make the minimum viable product or test out the ideas. And it's not possible to get, or it's very rare that you would have venture capital interested in that. So a lot of them borrow from their family members, or they might take small loans or use their savings. But angel investing is another way of really giving them that start capital to get going and get proof of concept. And it's very, very well structured in Denmark. You have angel investment clubs. They also teach you how to do it, because I only started doing angel investing about 3 years ago. I had no idea how to do it, but I took part in courses, and then being part of a community of other angel investors, I quickly learned how to do it. So and the other important thing is that the entire ecosystem values and appreciates what angel investors bring to the table, because they don't just bring the money. Many of the people who are angel investors have expertise in some way or the other, and this is what they bring to the startup, because startups, as they would say, they want smart money. They want people to leverage their networks. They want them to give them advice of how to do things in marketing and sales and different things that are necessary to get a business up and running. And so there are many opportunities where you can match angel investors with founders. There are several pitch events going on. I could go to one once a week if I wanted. And so the second part of your question, how can you bring this to the Caribbean? I think one thing about angels tend to invest in something that, apart from the fact that it's a good business opportunity, but it's something that they believe in, something they love, something they get excited about. So having that sort of almost personal relationship is quite important. And I think another way would be to, instead of saying, let's just bring them here, you have to find ways to bring the two communities together. The community of entrepreneurs in Barbados with the angel investing community. But I think, as I mentioned before, a huge untapped possibility is using the diaspora, because many of us want to contribute in some ways. And if you could set up a structure where Bajans and other people from the Caribbean can, one, learn about angel investing, and secondly, learn about the opportunities that exist to invest and bring the two communities together, I think that's something that could be very useful and fruitful.
Thank you, Dr. St. Hilaire. I don't see anyone approaching the microphones. Yes, please.
Yes, good evening, everybody. My name is Theodora Diacono, and I work at the EU delegation in Barbados, so you can imagine my question would not be on chemistry, but our work implies actually increasing the cooperation, including on research and innovation. So I would like to link on your presentation at the beginning, where you were mentioning that there is more potential for the European Union to be considered a destination for education, for research innovation. And I am referring now to my previous post, where I was working for Horizon Europe, and that is the biggest research innovation program in the world and the most open. So maybe you can help me make a pitch in favor of mobility and research innovation towards Europe, knowing there are many possibilities at the different levels of career. So if you can illustrate, perhaps, young researchers that benefited from these opportunities. Thank you.
Can I answer?
Yes, please.
So I think that's a very important issue, and we welcome people very much at the European universities when they come, in particular when they come with some sort of support. And of course, the Erasmus program is an open source for applying. They are really complaining that there's not enough applications for the program money. And that will open up the opportunities for making the evaluation of the talents that can then continue into a PhD study. Some of them will return home after the Erasmus, and some of them can be good enough that they can be considered for a PhD study in a European university. And these universities are, as I said in the beginning, just as high-ranking as American or Asian universities. So it's a good place to go, and they all speak English, so there's no reason not to go. I also think that the European societies are extremely helpful during your studies. So we have a different approach to the financials behind education than you have in, for example, the US, which is another advantage by going to the European countries.
I have a follow-up question with regards to that, but I do see Angela. Go ahead.
Hi, good night. Angela Aline, Senior Lecturer in Biochemistry. So I heard a lot of biochemistry tonight. Some chemistry, lots of biochemistry, peptides. And I want to congratulate you on your prize, of course, but I also want to ask that about the fact that many times as a scientist, we see negative results. And as you said, we sometimes might close that experiment off. But a negative result is also a result. How did you, in thinking about the click chemistry, realize that you had something there to continue working with? Or did you just
No,
put it
that-
down and continued working with it?
That was because I was really wondering how in the world can something as active as an acid chloride completely survive our reaction? Because we were trying to react this with an acid chloride. An acid chloride is an extremely reactive moiety, and nothing happened to the acid chloride, just made this five-membered ring, and then we could use the acid chloride reactivity afterwards. This actually started, so this is when I said, what? Something is going on here. And that is why I asked Christian Thorne to investigate the compatibility with all the biomolecules. And it was total, selectivity towards that reaction and nothing else.
So you continue working even though the results are surprising and strange.
Yes,
and
yes,
everything
and that taught me actually to always look for that, because that is where the novelty is. So whenever a student comes and say nothing works, that's a real opportunity.
Yes, thank you.
Thank you very much, Angela, for that question. And I have a follow-up question to that question, but I see people, Dr. Manning is waiting there, but I will have her wait 1 minute while I follow up Angela's question. So a lot of the times when we have students in the laboratory and you give them an experiment to do, they are very traumatized if it does not work out the way that it works out. And somehow we can find the words to let them know that that is okay, the fact that it didn't work, right? And I am happy today that you have said that a lot of the innovations come from things that you never expect.
Exactly.
That's where the novelty is. So I'm happy that you actually brought that up, and I hope there are more students.
Yeah, I would also like to say something that you won't like so much, and that is that the student should actually have the courage to tell you that, or me, that I'm stupid.
Sure.
Yes, and that this thing that we have been sitting there and designing on paper and pen behind the office desk, it's just not working because it's just we don't understand it really, and they find the understanding through the experiment, through the observation of what goes on.
That could be a challenge in our culture, as we very well know, the way that we are socialized. There is a lot of respect for your elders, so they will tell you, but they definitely will not come up and say, yeah, this is a stupid idea, this is just not working. They'll find another way to say it. Maybe they will take like no work Fridays, no work Thursdays, and when you ask them, they're like, yeah, well, that's not working out, so I had to go down to the beach. That's correct.
It's better to get it straight up.
I agree, totally. Dr. Manning?
Good evening, everyone. Thank you for the talks. So I am also a biochemist. Found the talks very interesting. But one of the things that we face, particularly at UWI, is the combination of pulling the science with the entrepreneurship. And that is something we fight because, as you said, we do have the fundamental research and then we have the applied research. What mechanisms in Denmark are utilized at the university level or at an earlier level to promote that concept of, you may not have something entrepreneurial now, but it's something in the future, or thinking entrepreneurial, because that is a different thought process in some cases when you're really stuck in the fundamental research. So what mechanisms are they using in Denmark to help students kind of bridge the science and the entrepreneurship?
So, you want?
Okay.
Okay. So we have at the universities in Denmark, all of them have a tech transfer unit. When you have an idea, or not an idea, when you have an experiment that seems to be very promising for something completely novel, you contact the tech transfer office and you get legal help to see if it's actually worthwhile patenting. If it is, it will be patented before you publish. And then you will go with this patent, for example, to an incubator that is close to the university grounds. That's called Bioinnovation Institute, or somewhere else in the very incubator positive environment around the universities. Where you then ask for laboratory space if that's needed. and they will evaluate your project and your patent and see if that's possible. If it is, you can get like 2 years or something like that to get to proof of concept. You'll get some support if you're lucky from BII, or you can get external investors, angel investors that comes in and helps you with it. So there's a whole, as Peter said, a whole infrastructure for innovation around the universities.
And in addition to what Morten said, many of the universities, they have entrepreneurial courses. So they teach the students already, even before they have an invention, that this is an option. For example, I mentioned Tempty Foods. They met actually at one of those innovation courses, and they had to do a project. So exposing the students to the opportunities and teaching them the process about the tech transfer office, the importance of patenting, it's one way of building their awareness. And many of the universities, well, there are not that many, I think there are like 6 universities in Denmark. Denmark is also not a small nation of 5 million people. But many of all the universities have an innovation hub. And there is a whole selection process. For example, I've already sat on panels where I evaluate some of the ideas from the students to see if they can continue into the innovation hub. But one of the things that there's increasing awareness of is that just because you're a good researcher does not mean that you'll be a good entrepreneur. And so it's important to understand where the strength of the person lies. And there have been several times where mistakes are made where they force an excellent researcher to try to be an entrepreneur. So this sort of, they offer mentors and guidance as to whether, after you've had an excellent idea, whether it makes sense for you to continue and be an entrepreneur, or whether somebody else, you can get a co-founder or another founder can take your idea forward.
Thank you.
The innovation is then also shared between the researcher, the students, and the university. If the university takes the entire development task financially, then it's 66% for the university and 33% for dividing between the inventors. And already at the disclosure time, you have discussed between the inventors, the students, the supervisors, so on, how is the contribution of each individual to the invention, and then any income that comes out of that is divided exactly according to those percentages of contribution.
But that's at Copenhagen University.
That's at Copenhagen, and it might be different in other universities.
Each university has their own split.
Great, thank you. I am happy to see that the university is the center of all this innovation, and I am sure that the innovation hubs that have been developed came about because of government policies. No?
It's also because of the funding infrastructure of Denmark.
Funding, that was the second one. Government's policies and funding.
Yeah, funding infrastructure in Denmark is a result of the very high taxation. That's very strange, but in fact, the success of Denmark is due to the very high taxation we had 20 years ago. One of the highest in the world, probably the highest in the world, actually. And that resulted in the government giving the companies exemption of taxation if they put the money into investment funds for investment in science and pay back to society. And all the big companies in Denmark are putting like 10-20% of their revenues every year into these foundations, which means that Novo Nordisk Foundation today is not only Novo Nordisk, it has about 100 companies that are part of their development portfolio, and they are investing broadly in science, in innovation, in startup companies, and so on. So it's a really, really active environment.
Yeah. And private foundations in Denmark play a huge role in the ecosystem. The government also plays their part. They fund different science clusters. They have a long-term strategic vision of how to foster innovation, because they're acutely aware that Denmark is successful because it's a knowledge-based economy. And so they put in policies and some funding in place to make sure that they foster innovation and education to be able to promote this knowledge-based economy.
This is also why the tribunal between the government, the industry, and education system is extremely important. If you want to establish that kind of ecosystem with this kind of foundation, funding system, you need to agree between the government, and enforce the positive trends in all these places, not act in competition about funding and so on. This is a societal task. It's not the task of the universities or government or industry. It's all of them coming together.
Thank you. I think we have a question. Good evening. A question or a comment, and let me first start by thanking Professor and Doctors. Your presentations were unexpected. I am nothing to do with science field. I don't operate or have that knowledge. So I was grateful for you making your engagements engaging. I think that was very useful and I wish I was able to convince my 16-year-old daughter, who I left at home, ironically, studying for her chemistry CXC. I clearly didn't sell the opportunity of coming here tonight sufficiently to her that she's not here. But I also want to thank the EU for the partnership to bring the opportunity to us in the way that you have. And ironically, that is where my comment or my question was going to be. And Professor, you kind of stole a bit of what I was going to say. Just part of my question was, is that collaboration? And you guys are ahead of the curve for us. We are quite far behind. And I guess we also suffer from our smallness, and we suffer from the partnerships that we're talking about, the opportunity to collaborate. But I think importantly, we also suffer from not having sufficient and proper data. So, Professor, you were sharing earlier, Doctor, you were sharing that Martina, Anna, and Cecile were able to access a bit of data, and they were able to connect the dots to make those things happen. You know, I think that we often have ideas. We often probably think they're stupid ideas. So your comment about making our educational system, for us it would be a transposition of it to make it more imaginative focus and less academic focus. I think it's something that would have to be a real cultural shift for us to embrace, but clearly that is required for us to be able to bridge the innovation that we need to step further. But I think importantly, we need the partnerships, we need the access to the data, and that rich, no shame partnership to have those fruitful conversations to be able to access the benefits that you're talking about. So I would like for us to be able to take away from here the idea of more rich collaboration, to really tease out the innovation and the creativity and the transition that needs to happen for us to be able to bridge the gaps.
Okay. So the reaching out from the EU, I think, is a very good first step in this direction. What you are missing in the process, in the infrastructure, in the way that it works here, is available, and there are actually an offer, in my opinion, from the EU to make the bridging that is necessary to fill out those these vacuums that you have. This is the starting point for collaboration. This is ideal, in my opinion, that this is a starting point, starting with your educational system, to see if we can provide some support there from Europe, but there's a whole innovation process coming after that, where I'm sure that I know that Novo Nordisk is looking around, for example, the foundation is looking around the world for investment, because we simply have too much money in that foundation to invest in Denmark.
Problems to have. So I just want to say that we talk a lot. We're very, very good at talking, but we fall down when it comes to execution. We are very slow to execute. So I would like to see some improvement in that area. And I think that we can start locally as well, where we as people can show that we have an appreciation for science. Yes, this is something that I find to be lacking in Barbados. And we know that our students or graduates or science graduates have difficulty finding jobs in scientific areas once they graduate. And as I was discussing earlier today, our science students have soft skills that can apply anywhere. And therefore we have to show as people some sort of reverence for science, because as was said today many times, that is the way forward. Nothing else. I think. Yes, sorry?
So thank you very much for your reflections. I thought they were very thoughtful. The one thing you said stuck with me. I think you said something about small, and I'm paraphrasing, that the smallness is a problem or something. It's a hindrance.
The smallness is a problem in that we don't connect well enough when we're so small. So we're very in our silos.
Okay, so that was exactly my point. I would say small size in itself, it's not a hindrance. It's the mindset and the approach, but I guess that's what you're trying to say. And I think when you are small, you have more of an incentive to do partnerships. And I think there's also a difference between being a small nation and a small market and trying to think and build products just for that market. Just because the world is so wide. I mean, when you think of many of the huge inventions that have been made, some of them come from small nations. And I will again go back to Denmark, because in terms of Europe, Denmark is a small country. We're under 6 million people, right? So, but when you think, small nations can think big and think beyond the borders. So that's what I wanted to add.
Okay, I think that's Dr. Garner O'Neill.
Yes. Hi, good night. Professor, you said something tonight that really clicked with me.
Oh.
No pun intended. But you mentioned about teaching chemistry at the early stages of education. And it really clicked with me because I teach a course, Fundamentals of Teaching Chemistry, and a huge part of that course is micro-teaching. And I say to my students, you could plan for your micro-teaching at any level, at any age group, but it must be about chemistry because it's a chemistry course. Inevitably, it is pitched at secondary school or tertiary education. Not many people could think about how we could teach chemistry at the lower levels, the fundamental levels of education. So I was wondering if you could give us some examples of when you talked about that, what really did you mean in that sense?
You're not being projected.
It's not connected, I know.
No.
I won't do it, but I have made some videos, small videos, where you see two happy hydrogen atoms bumping around, and they meet each other a couple of times and they find each other very attractive. So they make this common electron cloud around them. And you see they are very happy and they dance around and two other find each other, and you get a lot of hydrogen molecules out of hydrogen atoms. So 2 H dots, which is hydrogen alone, becomes 1 H2, where 2 shares a pair of electrons. And this is something that takes 2 minutes, and when it's done correctly by animators who can make the hydrogen atoms smile and be happy and look really good, then this is something that will stick, just as the Donald Duck cartoons you saw as children. They still stick somehow in your brain. This will stick with them for life. I also have a video where you go out and in of water cooking, so you just see the water bubbling, and you see the water molecules in an animation, how they move, first very slowly, completely stuck to each other's eyes, and then slowly, and then faster and faster, until they become air or steam, and they condense again on a lid of glass. And it's very simple to do. You can do this with modeling software that we use every day, and then some animators that put some emotions into it, some quality, some excitement, some background where everything goes on, and that's going to be extremely accessible for the young people, I'm pretty sure.
Thank you. We have 3 more questions, so let's see if we can get those 3 questions asked and answered briefly, very briefly, in about 10 minutes. Yes? 5 minutes. They're saying 5, but that means plus or minus 5 as well. So I think...
Hi. Good evening. Professor, I wanted to ask you about, you mentioned the medal, but you did not mention the cash prize.
Yeah, so that's a fixed price, independent on whether the financials goes up or down, or it rains or snows. It's always 10 million Swedish crowns divided between the people who receive the prize.
Right, so was it your portion, was it a personal prize, or did you have to share it with the university?
No, so that's a personal prize. You don't have to share it if you don't want to with anyone. You can spend some of them as a funding, and they're actually tax exempt. Wow. Because it's a real prize. It's because you did something spectacular.
Yes, you did. And the other thing is that, were you able to monetize your research in any way?
Yeah, so now you saw here in the corner 4 companies which took inventions from our research and progressed them into companies.
And you were rewarded as?
I was stupid, so I got a lot of money for one company, but I kept them in the company, and eventually the company was sold into another company and diluted, and suddenly it was just gone. So I should have sold it when it was on the top, so then I would have been very rich today.
I told him to.
I am this kind of, loyal person who is always very stupid when it comes to finance.
Scientists. So unfortunately, we are out of time. However, you will have the opportunity to speak to both Professor Meldal as well as Dr. St. Hilaire afterwards. Yes, so please keep your questions. Don't run away as we end, because I'm sure that they want to hear your questions, and they sit up here just like me wondering where did the time go? Yeah, we just started the questions, and I didn't get to ask any questions either. But that's it. So thank you very much.
So I am sure that you were very pleased with that question and answer session, and I'm really happy that we had some really insightful questions come in and some great answers. And at this point, all that is left for me to do is give the vote of thanks. So I want to thank a number of key persons responsible for the success of tonight's event, and I dare say the broader Connexeus 2025 Barbados edition. So special thanks, of course, to Professor Winston Moore and Her Excellency Ambassador for delivering remarks. Sincere thanks to Dr. Phaedria St. Hilaire and Professor Morten Meldal for your willingness to journey quite a long distance across the seas and to interact with us, and for a very insightful and relatable talk. I'm extending thanks to the Connexeus 2025 planning team, the FST, stands for Faculty of Science and Technology Ushers, UWI Marcoms, Marketing and Communication, and of course our host at the Sagicor K-Phil School of Business and Management for all that you have done to bring this event to a successful conclusion. And of course, finally, I want to thank you, our audience, both online and in person, for journeying out. Saturday night, it's always a tough sell, but you came, and I'm very happy that you are here with us. And I want to invite you now to, we have a cocktail hour. And so we ask you to stay, mingle, have conversations with us. Some of you we haven't seen for a while, so we look forward to interacting with you for a little while. Thank you, everyone, for coming. Thank you to the team.